Hi everyone, my name is Ulrich Steinwandel and I'm currently a Flatiron Research Fellow at the Center for Computational Astrophysics in New York. And let me maybe start by thanking the organizers for giving me the opportunity today to talk about my research on general research on magnetic fields. So I picked a very broad title for my talk, which is simulating magnetic field amplification within galaxies and galaxy clusters. And this is in principle exactly what I want to talk about today. And I hope you enjoy the talk. Okay. Okay, very good. It changed. Very good. Okay, so I structured this talk in basically two parts, and I want to start with the first part where I talk about the magnetic field, the galactic dynamo in the Milky Way, and numerical simulations of the galactic dynamo in the Milky Way. And the second part where I essentially want to extend this to larger scales and talk about the small scale turbulent dynamo in general in the intracluster medium. And when it comes to the galactic magnetic field, there are a lot of approaches that you can study this with. One that has actually proven to be very, very successful is direct numerical simulation. So this is exactly what I'm working on. And they're very different, a lot of different flavors, a lot of different codes that have the respective strengths and weaknesses. And we take our host code, my host code, Gadget 3, with a very, very newly updated smooth particle magnetohydrodynamics implementation. And we simulate a Milky Way galaxy, an isolated Milky Way galaxy at very fairly high resolution. And on the left, you can see the setup, or yeah, on the setup of this simulation, where we basically have a galaxy that consists out of a stellar disk, a gas disk, and a bulge that has been modeled with following the prescription from Springer et al. 2005, which is surrounded by a hot halo, the circumgalactic medium, and dark matter halo, live dark matter halo in that sense. Yes, and the addition in our simulation is that we really try to model this circumgalactic medium as realistically as possible. So the resolution in the galaxy is the same than in the circumgalactic medium. It's around 4,000 solar masses in both cases per particle, which is fairly high resolution. Gives us also fairly high resolution in the circumgalactic medium, which we basically model with a beta profile as it is observed from X-ray observations, for instance. And when we actually simulate this, so we have two base models, one where we basically put a constant magnetic field in some direction. We usually pick the X direction, fairly low one of 10 to the minus 9 Gauss or something like this. And we have a second model where we actually inject the magnetic field energy with the supernova feedback that we have in the simulation. And the idea is basically, I tell you what happens beforehand, because I only mainly want to discuss the supernova seeding simulation because it's the more realistic model. There is not a big difference. Essentially, there's not a difference at all in the global evolution of the disk. And what you will see in this movie is on the upper row, you have like the phase-on view on left density and right magnetic field. And as this is the seeding case, there is no initial magnetic field because there are no supernovae, right? And on the bottom, you can basically see the edge-on view. Left is density and right is magnetic field. And if we watch the movie, actually what happens is you can see that the disk builds up a beautiful micro-Gauss magnetic field that is, yeah, it's a global disk magnetic field. And the interesting thing is that we drive an outflow based on the magnetic field in this kind of simulation. And I want to discuss two things on the galaxy scale simulations: A, how we get the magnetic field, and B, how can we explain that outflow. Both are very interesting questions. And I don't have the time to go into details of all of the well, things that happen in these simulations. So I give you a brief overview on magnetic field amplification in the simulation and on the outflow process itself. So let's start with the magnetic field amplification, because we first need an equipartition field to explain this outflow, for instance. And a very popular theory that has been proposed already quite early on by different people. For example, Kreichnan in 1965 and Consumptive in 1967. It's the theory of the small-scale turbulent dynamo. And the idea generally is, and I brought a small rubber band to like visualize this. I'm not sure if you can see that well or not, but I tried anyway. So the idea is that you have turbulence in your interstellar medium, or later in the intercluster medium, when we discuss the galaxy cluster magnetic fields. But the process itself, you have some turbulence and you have a magnetic field line, which is this rubber band. So what turbulence is doing, it's like stretching it, it's twisting it like this, and it's folding it over. And then you get a configuration which looks like this. Of course, in reality, don't touch itself, but you can realize this when you do that with a rubber band, that you build up some tension. And this is actually really, really important, because when you repeat this process, it will become harder and harder to actually stretch the rubber band. And in reality, it becomes harder and harder for the turbulent motion to stretch, twist, and fold magnetic fields. So you produce a tension force, which is counteracting the magnetic field growth and finally saturating the dynamo in the nonlinearity. And you can quantify this dynamo process. And the easiest way to quantify it is over so-called Consumptive power spectra, which you can see on the left for my magnetic field models in the galaxies that I have. And generally, we recover this K to the 3/2 power spectra quite well. Yes, you can say it's noisy, and that's true, but we still get the shape right. On the other hand, you can quantify dynamo over this tension force, because as I told you with the rubber band, it's essentially you expect that there is a force based on the tension force of the magnetic field. So, and what this means in general is like that you limit the curvature of the field lines as a function of field strength, or the other way around. You get a specific field strength as a function of the magnetic field line curvature. And this is what you can see here on the right, where we plotted this in red for our supernova seeding model, and in blue for our primordial magnetic field model, and compared with the predictions of very, very high resolution simulations of the ICM. So it's subsonic turbulence. So there's a caveat already for galaxies, because there you might expect supersonic turbulence. But it fits quite well with these high resolution subsonic turbulence simulations of Scheckchen et al. 2004, which is actually, in the theoretical sense, correct, because the Consumptive theory operates under the assumption of subsonic turbulence. So, and this works quite well, and it also works actually quite well in comparison to a galaxy cluster. And this is what I personally find so fascinating, and what we come to in a bit when we talk about the ICM magnetic fields. Before we do this, I want to briefly explain to you, very, very, very broadly explain to you how this outflow mechanism that you witness could work. And I want to put this first, because we're like the only people that find such a strong effect with magnetic fields. So of course that is like to a degree problematic, but it's not a very strong outflow. Okay, so that's the first thing. Like it's nothing that can. It's at peak, it's like a solar mass P, but this is peak. So usually it's below, and settles around 0.1 solar mass, 0.05 to 0.1 solar masses in the outflow rate, which is not very large compared to regular Milky Way outflows. But it's there, and we can try to explain it. And then we can obviously discuss in the discussion how physical this is. I think it is physical. I wrote a paper about this, how physical it is. So the general idea here is that you first need to get your magnetic field into the range where it's like saturated. That means you saturate it early on with a small scale turbulent dynamo. You can then switch the small scale turbulent dynamo off when you have an equipartition field of like a few microgauss, a few tenths of microgauss, depends where exactly you are in the galaxy. And then in the movie, we saw that there's a bar formation process going on. And actually what's happening in this simulation is that this bar is funneling a lot of gas to the center. This drives another dynamo process, or another quick dynamo, because you essentially expect, so the bar is so you have radial motion alongside the bar, which is sheared by the larger scale rotation of the disk, which is not very high in the center, but it's still there. And then what happens is you get an increase in magnetic pressure, which is together with the pressure that's provided by the supernovae that deposit energy in the center, is leading to a rise of magnetic field lines, i.e. this is called the Parker instability. And as soon as these field lines hit the edge of the disk, and this is like illustrated here, we get these very, very nice Parker lobes in the magnetic field structure, which you can see here. They break free and they move freely into the much lower density CGM. And this is in principle very, very broadly how this mechanism works. In my last couple of minutes, I want to actually discuss a little bit more on dynamo, but on larger scales now. So as you might have seen from the curvature relation, we overplotted a galaxy cluster, and it's kind of interesting that this works. This curvature relation seems to work similar in a galaxy than in a galaxy cluster. So you can obviously also go straight forward right ahead and do simulations ab initio, first principle simulations of magnetic field amplification in the ICM. So what we do here is like we run very high resolution galaxy cluster simulations down to redshift 0. And we investigate the magnetic field amplification as a function of resolution. And we did this in my paper, my most recent paper. We did this for 3 different resolutions, which we label as 1x, which you can see in blue, 10x in red, and 25x in magenta, where 1x refers to a mass resolution of like around 10 to the 8 solar masses in a very massive galaxy cluster with a really mass of 3 times 10 to the 15 solar masses. So this is one of the most massive objects that you can imagine to find anywhere in the universe. So it's numerically quite challenging to simulate those. And what you can already see is like there's something going wrong with the 1x simulation. So this has a very different shape than the 10x and the 25x, which have like 10 and 25 times higher respective mass resolution. What you can see very nicely is that we get suppressed magnetic field growth in the 1x case, where we have this corresponds to like let's put a number on this, like 0.7 gigayears e-folding time, for instance. What works better is when you go to higher resolution and you actually resolve more of your turbulent cascade in the ICM. So you resolve more of your small scale motions, then you also saturate earlier. And the interesting thing is that this happens in the 10x and the 25x case for around redshift 2 after like a couple of gigayears of evolution of this cluster. And the interesting thing here is that this corresponds to like an e-folding time of around 100 megayears, which is very consistent with the theory of the small scale turbulent dynamo. And what's even more interesting is that the magnetic field is higher at higher redshift, which is actually what you expect on larger scales from the RM signatures, which is also consistent with like predictions that were made for SKA, for instance. So we're doing something right. I don't think we do everything right, but I think we're doing something right in these ICM galaxy, full cosmological galaxy cluster simulations. And at the end, what you get is a full-fetched magnetic field at redshift 0 within the virial radius, which is very, very nice. And you can do the exact same experiment that we did on the galaxy scales and look at the two priors we defined, which is on the one hand side the power spectra that you can see on the left, and on the right hand side you can see the curvature relation. And you see in both cases, again, it works. So we're doing something right. Bigger question, and this is the one that I want to end with, is specifically why does this curvature relation work so well? Because this is nothing that you would expect. So this is maybe a good point that we can discuss in the discussion session. Why a relation like this curvature relation that was basically constrained by high resolution ICM simulations is doing such a good job still in a much more complex, fully cosmological environment of a galaxy cluster. And it seems to work quite well. So that's something it's puzzling for me, that I don't fully understand yet. So I'm happy to discuss this with everyone. And with that, I'm coming to my conclusions, and I basically want you take these 3 points. I wanted you to take these 3 points away from my talk. We have shown that we can get efficient magnetic field growth by a small-scale turbulent dynamo, both in galaxies and in the ICM. We quantified this with magnetic power spectra, as well as magnetic tension force. And on top of this, on galaxy scales, we propose an interesting mechanism for how we can drive outflows that are driven by the magnetic field itself. And I forgot to mention this earlier, but the interesting thing that we related this to is that might actually play an important role in local spiral galaxies, because in the changes sample, people observe these X-shaped halo fields, which our process produces naturally. And we double check this with the changes sample, and there's like 22 barred spiral galaxies that are classified as barred spiral galaxies, from which 17 have an X-shaped halo field. So this is just an interesting fact. I'm not sure if it means anything, but we can also discuss this in more detail in the discussion session. And with that, I thank you very much for watching the video, and feel free to ask me questions prior to the discussion session on Thursday, and I'm very, very happy to see everyone there. With that, thank you very much, and I'm very happy to take any questions at any time.